Every day, the sun rises and the sun sets. Seasons change. Snows melt and flowers bloom. Time marches on. Some rivers run dry while others crest their banks. Some forests grow while others burn. Earth is a planet of constant change. Cities expand, coastlines shift, volcanoes erupt. Tracking these changes, be they subtle or profound, is critical to our understanding of the health of our planet. For nearly half a century, the Landsat program has been at the forefront of monitoring Earth's ever-changing surface, providing an unparalleled record of our planet's land use, vegetation cover, and natural resources. From tracking deforestation in the Amazon to monitoring water quality in the Chesapeake Bay, Landsat data has become the foundation for understanding Earth's ecosystems, paving the way for many other remote sensing missions. In recent years, a new player has emerged in the world of Earth observation: Europe's Sentinel-2A and 2B satellites. Part of the European Space Agency's Copernicus program, the Sentinel-2 satellites, launched in 2015 and 2017 respectively, circle the Earth and continuously collect data from the planet's surface, much like Landsats 8 and 9. The beauty of these two satellite systems is that while they are complementary, they each have unique strengths. While the Landsat program provides the longest continuous record of Earth's land surfaces, Sentinel-2 offers more frequent revisits and additional spectral bands, taking a complete picture of the planet every 5 days. But what if we could bring these strengths together? That's exactly what NASA's Harmonized Landsat and Sentinel-2 project, or HLS, aims to do. Imagine trying to put together a puzzle, but the pieces come from two different puzzle sets. The HLS project is like finding a way to make those pieces fit together seamlessly, to create one unified picture. HLS is a deliverable of the Satellite Needs Working Group, an interagency effort of the US government dedicated to identifying and addressing Earth observation needs across US civilian federal agencies. With global production of HLS data being led by NASA's Interagency Implementation and Advanced Concepts Team, or IMPACT, the HLS project takes the raw satellite data from each mission and puts them through a series of algorithms to make them compatible. The algorithms remove atmospheric effects, such as haze and cloud cover, adjust the imagery from each satellite to perfectly align, accounting for varying sun angles at different times of the day and year, and fine-tune the spectral bands to calibrate the colors between the satellites. The end result is a harmonized Landsat and Sentinel-2 data product ready for analysis that provides a snapshot of the Earth's surface every 2 to 3 days on average. A powerful tool with the potential to help farmers optimize their crop yields, city planners more efficiently map urban growth, and forestry managers more effectively monitor the health of our forests, among many other uses. Following the initial release of HLS in 2018, it didn't take long for researchers to take advantage of the high level of spatial and temporal detail provided by the product. A paper published in 2020 by a team led by researchers from Boston University aimed to test the effectiveness of using HLS data to track annual vegetation growth cycles, also known as seasonal phenology, across North America. Every year, plants across the continent sprout leaves and flower in the spring, peak in the summer, and, come autumn, change color in fall as the winter approaches. Small variations in the timing of this annual change, however, can have ripple effects, impacting how plants absorb carbon dioxide or how nutrients cycle throughout the ecosystem. Some insects and birds, for example, time their life cycles and migration patterns based on when plants emerge in the spring. In the past, satellite imagery has been a key tool for tracking seasonal phenology, but the coarse temporal resolution of the data has limited the detail and accuracy of the analysis. But researchers believed the detail afforded by Harmonized Landsat and Sentinel-2 data could be the answer to these challenges. They developed a sophisticated multi-source land surface phenology algorithm and fed it HLS data from 2016 to 2018. The results were impressive. Applying the algorithm across North America, the researchers were able to track vegetation phenology at a level of detail through time and consistency never before possible. They could map out the greening and browning of vegetation in incredible detail, observing differences not just on a continental scale, but even within single fields and forests. And they were even able to observe how elevation in Tennessee's Smoky Mountains affected the timing of leaves emergence in the spring. Researchers believe that, going forward, their algorithm could have a wide range of potential applications, from precision farming, helping farmers increase crop yields, to monitoring our ecosystems, allowing conservationists to make more informed decisions about the timing of controlled burns. Every year, thousands gather in the spring to witness the cherry blossoms bloom in Washington, D.C.'s tidal basin, or in the fall to take in the vibrant Vermont foliage. Seasonal changes everyone can look forward to. But other seasons, such as the Atlantic Ocean's hurricane season, fail to generate such enthusiasm. Every summer, the warm waters off the coast of Western Africa create the perfect breeding ground for spawning hurricanes. Storms that travel west across the Atlantic, with some developing the potential to wreak havoc along the eastern coasts of North and South America. States like Florida are no stranger to these devastating hurricanes, with coastal communities contending with violently high winds and damaging storm surges on an annual basis. Quickly locating and assessing the extent of damage and the aftermath of a hurricane can be critical in aiding search and rescue operations on the ground, especially if you're getting help from high above in orbit. In September 2022, Florida fell directly in the path of Hurricane Ian, a Category 5 hurricane with wind speeds topping out at 160 miles per hour, causing damages estimated at over $100 billion. In the aftermath, environmental researchers at the University of Connecticut sprang into action, leveraging HLS data to create a near real-time map of the damage caused by Hurricane Ian. Building on previous work the team had done with Landsat data, the researchers developed an algorithm that could sift through the massive HLS dataset and detect even subtle changes in the satellite imagery, allowing them to map out the areas that were likely damaged by the storm. As soon as the research team had access to the first clear satellite imagery following the storm, they were able to put their system to work. The open-source disturbance map was released to the public just days after the storm, highlighting areas where damage was likely to be most severe, allowing rescue teams to prioritize their efforts. By harnessing the power of Harmonized Landsat and Sentinel-2 data, these researchers were able to provide yet another example of how advanced remote sensing techniques and open-source data sharing can have a real, tangible impact in emergency situations. Whether it's giving us insight to the seasonal changes of our planet or helping us respond to natural disasters, the Harmonized Landsat and Sentinel-2 project is a potential game changer in the world of Earth observation. By combining the strengths of two of the most advanced satellite systems, HLS data is providing us with an unprecedented view of our ever-changing planet. But the future of HLS isn't just about more data, it's also about making that data more accessible and actionable. HLS data scientists are working on developing new tools and platforms that will allow users to easily visualize, analyze, and share harmonized Landsat and Sentinel-2 data. With projects like HLS lighting the way, the future of international cooperation for Earth observation is bright. New missions with enhanced spatial and temporal resolution throughout the electromagnetic spectrum will offer fusion capabilities to provide unprecedented information about our Earth system. As the project continues to grow and evolve, it will undoubtedly play a crucial role in our efforts to better understand and protect this incredible planet we call home.